Hello everyone. I will presenting Escaping the Multicall of Madness. Maybe you know Multicall. It's a contract that you can call and it executes multiple transactions or if calls for you. I will explain more of this later in the talk, but first a bit about myself. So, well, I'm already doxing myself, so I'll take off the glasses. And yeah, hi, I am Marco. I'm a full stack developer. I do mostly front-end work, a bit of back-end work as well, and I like to call myself the front-end developer of the back-end, which means I like to do API design, doing like performance, caching strategies, and so on. And this also includes when you access like data from the chain, because maybe you know that it's very hard to get like bulk data because you can only always execute like one function. I'm a serial hackathon enjoyer, which means I'm like at mostly like all the big hackathons, like ETH Berlin. You see the picture there. We were doing our society. We won like the grand prize, and our project was basically just redistributing the prize money across all the participants of the hackathon, which was really funny, and people liked it. They voted for us. It was like a publicity vote. You can follow me on Twitter, on whatever, Lens, Mastodon, Blue Sky, Farcaster, everything that you want. And let me shill a bit my projects that I'm working on. So my professional job is Astaria. It's an NFT lending protocol. So maybe you know it, like there's now Blur doing it, Binance announced that they're doing it. There are like a bunch of projects. We're doing it a bit different. So what we're doing is we do fixed term borrowing, which just means like the interest rate and the length of your loan are fixed. So you know exactly like when you have to repay it. And we have what we call a three-actor model. So that means next to the lender, which usually defines the terms, so how much they want to give away for how much interest, and the borrower who provides the collateral, like an NFT, a Bored Ape or something. We have a third party, which is the strategist. And the strategists, they are just generating the terms and competing with one another for liquidity. And you can read more at the docs. And our public beta is live as of like 3 hours ago. So if you have a blue chip NFT and you want some money, then you can provide us as collateral. And if you have liquidity, like some money laying around, some ETH, come talk to me. We want liquidity providers. My other project is Ferry. We're doing infinitely scalable raffles, which means if you do like an allow list giveaway or an NFT giveaway or something where you need more than one random number, we have like a very nice contract, a very nice algorithm, which is basically like super cheap, and you can do like from 1 million participants, you can have like 100,000 winners or something, and it's basically the same as if you were raffling for one winner. It's really cool. You can also read more about the technicalities at docs.ferry.dev and talk to me if you want to do some giveaways or some randomness. So, the talk itself. Let's talk about finding your ETH calling. Small joke. So, how do you get data from the chain? Well, we have the standard way that everyone knows. So here in this example, I want to display like how much USDC or how much of any token a user owns. And to do this properly, we have to do 3 calls. We need to get the balance first. So that's the USDC balance off with some address as the parameter. Then we have to get the decimals, because while Ethereum has 18 decimals and most tokens do, USDC, for example, has 6. So we can't just put 18 as a fixed constant there, but we have to get it from the chain as well. And then we get the symbol as well, so we can display it. And when those 3 calls are done, then we can display. So this is probably how most people know it and how most like amateurs do it. And the problem here is that we have 3 API calls, 3 requests, which are basically like waiting for each other. So you have one request, then you have the next request, then you have the next request. That's what we call a network waterfall, and it looks really bad and it's not a good user experience. So we have the next level, which is parallelization. So in JavaScript, we have this promise.all, which basically can fire like multiple asynchronous requests in one. And then they are running at the same time. So that's much better experience than waiting for one call, but we're still doing 3 calls here. And wouldn't it be nice if we just could do one call which includes all 3 in like one request, right? So we have an honorable mention here, which is the JSON RPC batch provider from Ethos. You don't need to know about this, and I don't know if you should really use it, but basically it's taking multiple calls to the Ethereum node, and it just batches them together if they are happening like same JavaScript event loop. Don't need to know about this. But basically it does magic stuff so that your requests are a bit more optimized. The problem with this is that your requests can still happen in different contexts. So for example, if there's a new block coming in and the node starts executing like one request, then there's a new block, then suddenly you have a different context for your request. So we don't want that. We want all our calls in the same request. So that's where we go next, which is the multi-call way, which is like the standard, I guess, for getting like batch data from the chain. So what we do here, we use a library called Ethos Multicall, and we basically do the exact same thing where we instantiate the provider, and then we do a multicall provider.all. So instead of a promise.all, we do a multicall provider. And what this does, it's like sending the stuff together as basically one request instead of 3 different requests. It's one request that contains all of them. So how does this work? Freaking multicalls, how do they work? So there's actually a contract deployed on, I guess, every EVM chain that exists. And it's always at the same address. It's this 0xCA11. Well, if you read it, it says Kaul, and it's at the front and the back. It's really cool. And what this contract does, basically, it takes multiple call data. So call data is like the request, what you want from the chain, which function you want to call. And it combines like as many as you want until you hit the gas limit. And it combines them into one call. And then it gives you like all the data. Can also do some cool stuff, like if one of them fails, you can tell it that, hey, it doesn't matter, it fails, but please continue anyway. And you can also get some like data in the call, so the block number, for example, so you can do caching. So I see you and you're like, yeah, we already know this shit, so what's more? Like, what else can we do? You know, like, what about if we have dependencies? So in this example, we're using ENS, and we want to resolve like the primary domain of an address. So what we do here, we do some like magic to get a node, and then we get the resolver of the node. So this is the first request, and we can't do any multi-call here because it's one request, and before we can do any other request, so in this example, we want the name and the avatar for the user, so the ENS name, something.eth, and the avatar, which is a IPFS URL, for example. But we can't do multi-call here. We can do like a name and avatar multi-call, but then it's still dependent on the other. So that's weird. And with like multi-call, there's nothing you can do about it. And you have to write the waterfall. You can do some optimizations, but it's still not like great. So I've actually been working with the Flow blockchain for a while. We're talking about different blockchains here, which is using Cadence, so their own language. And Cadence and the Flow blockchain, they have a really cool feature, which is called scripts. So scripts basically are code that you send to the access node as a read call, and then it executes like actual code like in the FVM context. So in this example, I'm using find, which is the ENS clone on Flow. And here we do the reverse lookup to get the name. And then we get the profile for the of the address, which is like the general profile where you can get like avatar, name, email, and so on. So hey, we can do this in Flow. Why can't we do it in Ethereum, right? So how do you do it in Ethereum if you want to get like more data than just one function call? Well, you have to do it like multicall, and you have to deploy a helper contract. So you take a contract, you write the logic you want here. So this example is like an ENS helper, which basically gets you, like, for an array of addresses, you get an array of ENS names, so kind of what we did before. And they deployed it on this address, on Ethereum mainnet, and, well, it works, so it's nice. But, well, you have to pay money to deploy the contract, and every time you want to change your helper, you have to redeploy it, and you have to pay money again, and on Ethereum mainnet, that's bad. It's very expensive. So, like, what else can we do? Well, we have ethcall, right, like what we've been using before. And with ethcall, you can also simulate contract deployments. So why not just put our whole logic in the constructor and return it, and that's good? Well, contracts, they just can't return stuff. I don't know why. Maybe someone can explain it to me, but contracts in Solidity can't return data. Well, or can they? Because we can do a little bit of assembly magic and basically force it to return data. And this works by, well, we first encode the data so that the types are really nice to work with. And then we do this assembly magic here, which is where we do where the 0x20 add to the address of the encoded data, which is basically getting rid of some, like, header of the returning object or the returning memory. Then we just tell it, hey, just return, like, the whole memory from when we encoded the data. So just return the actual, like, stuff, the actual memory. And even though, like, contracts don't support it natively, with this, we can just return anyway. And the nice thing is that if you look at the front end, it's working exactly the same as if you did, like, a regular call. So in this case, we instantiate the helper factory or the contract factory, which is basically just preparing, like, the code that you can send to the chain to actually deploy the contract. But we're not, like, doing a transaction, so we're not actually deploying it. We're just doing an ethcall, which is simulating, basically. And then we get some data, which we can then, again, decode. So we know that here our return type is an array of strings, and here we just decode the array of strings, and we get the actual strings. So, hey, we can do on-chain computation. Nice. So, well, now you think, okay, but this is a bit weird because I have to know my types, and I have to always, like, write a contract first, and I have to write a front end, so I need to keep the types in sync. Well, actually, you don't, because we already have typing solutions in front end. So ABI type, for example, is being used by WACME, so that you provide, like, an ABI object, and it will just auto-generate at runtime the types that you need. It's really nice. Or we have a type chain, which can generate TypeScript files and types for your contract. And then you know, like, all the functions on your contract, you know all the outputs, you know all the structs that you use. So how do we use it? Well, here we have actual code from Astaria. Well, I don't care if you steal it, but I can show here. So this is, like, we have the vaults, which are, like, contracts that you deploy, and they hold your funds and all the logic and so on. So what we do here, we have a helper function, get public vault display data down here, which is basically, if you remember the ENS example from before, you can, like, you have a function that you call, and then it returns you data. This works if you have, like, an already existing contract. In this case, we could also just deploy this contract and use it on-chain, but we don't have to. We can just use our assembly magic here and just force the constructor to return. And because we still have this extra function, which has, like, input types and output types, and types chain or ABI type will pick them up, we actually can go in our front end. We can basically use the generated types chain code, which is, again, a helper to deploy the contract, plus we're getting the deployed instruction with the parameters. And then instead of doing, like, a manual ABI decode, we can use the generated helper function, which is, in this case, decode function result. And this basically just transforms the data into an object which has like named keys. So like if you look back at the struct that we have defined here, vault address, vault balance, total shares, this object will also be available like this in the front end. So we have full like end-to-end typing. We have a Solidity contract, which is the source of truth, and we have in front end generated code, which represents the exact contract and the exact function calls and logic. So this is really nice. We can do like full end-to-end typed execution on chain, well, in an if call. And we can basically like ask any contract on the chain for any data that we want. So that sounds too good to be true, right? Well, there are a few drawbacks. So, well, I have the three main ones here, which are one EIP 170, which is basically just a hard limit on the code, on the size that a contract can be. It's 24 kilobytes, but it will take you a long time until you hit it. Then you might run out of gas, which is a weird thing because like there is a kind of hard limit of 30 million gas that you can spend because that's the maximum limit a block can have. But then every node can just like define themselves how much gas they want to allow. So some of them are as low as like 5 million gas, while others are, well, my prototype here is Alchemy. Alchemy is like, yeah, whatever, we do 500 million gas. So you can do a bunch of computation. So like our logic with the public vault data, we tried it with like 100 vaults and it was still fine. But then if you try to execute this on Infura, for example, they will say like, yeah, no. So you need to test and try to find like the best provider for this use case. Then the other problem is, if you use like ethers or you do some blockchain stuff in front end, you will see that your bundle sizes, they get always blown up. Like you have like multiple hundreds of kilobytes of data suddenly, or bundle sizes, so the JavaScript is being downloaded, because you need to download like all the ABIs of every contract that you interact with if you want to do it properly. You could always just take a small part of it, but like the nice thing is if you have like the full contract typed. And when in this case, we have an extra problem that we also have our actual bytecode of the contract because we need to fake deploy it. So we also have our bytecode in the bundle. So we have even more content. So you can fix it by, for example, taking all this stuff and putting it in a serverless function or like some API route on your server, so that basically the bundle size is not on your client's browser anymore, but it's somewhere in the cloud. And this is much nicer. You can also do some caching, for example. So this whole thing, the whole talk, the whole idea came from two people. They are, well, Dr. Gorilla.eth had like the first like idea, I guess. I don't know if she was the original like creator of this assembly hack, but well, this is the first time I read about it. And then libEVM took this and put it in a contract and put it in an article, built like an example contract, an example script, how to read it, and that's why I learned about it. And I basically built on top of that and added like the full end-to-end typing solution as well. So, well, that's it about on-chain computation. So now we know about so you know about the 3 levels of basic computation, which is just do one call each, do them in synchronous calls. You can do a multi-call, and then if you do even more, if you need even more computations, or you want to do like calculations, for example, like do big number division or something, or you want to request from like 10 different contracts in one call, well, just fake deploy a contract. So, thank you, and follow me on Twitter, Lens, Mastodon, Blue Sky, Farcaster, Discord, Telegram, email, Facebook, no. ICQ, I don't know if I still have access to this number. And don't follow me in real life, please. Thank you.
Hello. Thanks a lot. Yeah, that was an awesome presentation. Do you want to do a couple questions maybe?
Yeah, sure. Sure.
Any questions for Marco?
Yeah. So the question was like, well, why can't the contract return, and how do you get around it, right? So, so the thing is that, like, I can go back to the slide here. So this is like the constructor of a Solidity contract, and in Solidity, just the constructor can't return data. That's just a hard limitation of a contract. I am actually not sure like why this is. I wanted to research it, but I only finished the slides like 6 a.m. this morning, so I didn't have time to research anymore. But yeah, it's a hard limitation of Solidity. The constructor can't return data by default. So what we need to do is we need to implement this assembly hack, which basically forces the code to return something, even though the Solidity language doesn't support it.
Just the theoretical alternative would be to use this multicall thing and kind of in the first call deploy a contract and in the second call call the contract.
Well, like multicall, you could do like a contract deployment with multicall. There is like a transaction functionality, so you could actually deploy it to the chain. But then you can't do like, if you require, for example, the contract in the second call, you don't know it because it's like one. It's well, okay. If you know the address in advance of create2, then you can probably do something. But with this, we don't even need multicall. We just do like a fake deployment of a contract, and we have like an immediate return.
Cool. Any last questions? Sweet. Thanks a lot, Marco.
Thank you.